Everyone, welcome to in this lecture. So I'm going to discuss about the Thevenin theorem in this lecture. Before going to discuss this Thevenin theorem, let's share my screen. So let me introduce first myself. So my name is Arjun Kumar, and currently I'm working as a postdoc researcher in University of Trent in Netherlands. And before joining this university, I also worked as an associate professor in Bennett University. Currently, I'm on the sabbatical from Bennett University. So now let's discuss the Thevenin theorem, and we will discuss how to simplify or analyze any complex circuit by using this theorem. So in this lecture, we will discuss about the theorems, network theorems, and what is the use of Thevenin theorem, and what are the steps involved to solve any complex circuit by using this theorem. And an example will like solve the example and see that what are the process involved in the solving the uh, circuit element by using the Thevenin theorem. So as we know that why we require this theorem, because any complex network, it has like multiple elements and sources. So in a particular element, if you want to find out a voltage and current, then you need some techniques to simplify any complex circuit. So these are some theorems that are like Thevenin theorem, Norton's theorem, superposition theorem, and maximum power theorem. These are the popularly known theorems that is applied to find out the voltage and current in a particular element. All right. So like if you're going to like see the name of the Thevenin theorem is suggested from the name of a French engineer. His name is Leon Charles Thevenin, and he invented this theorem in 1883. So according to his uh, statement that any linear and bidirectional network can be converted in a form of a single voltage source and with the series resistance. If you have a like any fixed network and you have connected with a variable load, so thus the whole circuit, the fixed network, is converted in form of a Thevenin voltage source and connected with the series Thevenin resistance. So if you see the voltage across the terminal is called Thevenin voltage as seen in the figure, and the resistance that is looking from the open terminal of this network is called the Thevenin resistance. The question is that why we require this theorem. Like, so if you see in any complex network, we have a fixed terminal and there is a load. So if you change the load every time, then every time you have to do the analysis to finding the voltage and current in that particular load. Right. So the Thevenin, the advantage of this Thevenin theorem that you can fix the fixed network that will be converted in form of Thevenin voltage and series connected Thevenin resistance. And later on, you can connect your variable load, and you can easily find out the voltage and current in that load by applying the KVL and KCL. All right. So what are the steps that we have to follow to simplify the circuit to find the voltage and current in a particular element? So like first we're going to find the RTH, that is called Thevenin resistance. So in step one, we see that which element we have to find out the voltage and current. So make it open. If there is a voltage or the current source in that network, so first remove that source. So if there's a voltage, make it short. And if there is a current source, make it as open. And then looking from the open terminal, you can find out your Thevenin equivalent resistance. So this is the first step, is the first part that you have to find out. And the second part, that is you have to determine the VTH. So how to going to determine the VTH? Again, we have opened the terminal where the load is connected. And then at that open terminal, we will going to calculate the voltage. So that open terminal voltage is called the Thevenin voltage. So once we will have this both RTH and VTH, then we can convert in form of a Thevenin equivalent circuit. So let's see how to calculate the voltage and current in a particular element, or that is called load, that is variable. The remaining element are the fixed. Okay, so this is one example here. How to going to find out the Thevenin theorem by applying the Thevenin theorem to find out the voltage current in this load resistance, that is RL. Okay, so just a moment. Yep. Okay, so the step one, we have to find out the RTH. To find RTH. Okay, so what we will do, we have to remove this load first. Okay, this terminal become, once we'll just remove this load, it become open. It will be your voltage source and the resistance. And this is the resistance. Now you can just redraw this circuit like this, and this will be your open terminal. Okay, so this is your 2 ohm. This is 2 ohm, and this is 4 ohm. This is 4 ohm, and this is 4 ohm. All right. Now you can see here is a voltage source, right? So if there is a voltage source, make it short. If there is a current source, you can make it as an open terminal. Okay. So here's a voltage source. So what we will do, we just simply make it short. Okay. So it will be short here. Now you can see this will be 2 ohm resistance. And we have 4 ohm. Okay, so this is your open terminal now. Now, if you're looking from this side, you will see that this 2 ohm resistance and this 2 ohm, they are in series and parallel with this 4 ohm. Okay, so if you simplify the circuit, this will be like this is 4 ohm resistance, because these 2 and 2 will be in series, so it's become a 4 ohm. Okay, and then you have this 4 ohm resistance. And you have this 4 ohm and 4 ohm. Actually, there is no resistance. This is only simple wire here. So it's a 4. Okay, and now you have the terminal A and B here. Okay, so we have to find out this equivalent, that is our RAB. So this combination is again parallel combination, right? So this is a parallel combination. Then you can write as a, so it's parallel is 4 into 4 upon 8. So you can write this 4 and 4 become, to simplify this circuit here again. So it will be your one resistance. This is 4. This is 4. So this value, this parallel combination is 4 into 4 upon 8. Right? So you can simply write as a, it will be 2. Okay. So this will be your 2 ohm. This is your 4 ohm. Now this 2 ohm and 4 ohm in a series and parallel with this 4 ohm. So you can write this 6 ohm, or you simply write here, that is 2 plus 4 ohm is parallel with the 4 ohm. All right. So this is your RAB here again. If you solve this combination, it will be your, if you write here, it will be 6 into 4 on 10. Okay, so it will come around like 2.4 ohm. So this is your RTH. All right, so this is your RTH. Okay, now we have to find out the RTH. Now the next step, we have to find out the VTH. Okay, to find VTH. So again, what is the case? First, we just write the voltage source here. Okay, this is 2 volt, and this is, I guess, is 12 volt. Yes, so it's a 12 volt here. Here you have 2 ohm resistance. And there's a 4 ohm resistance. All right, and so again, here is a 4 ohm. And this is the open terminal. Okay, so we just have the remove the load. So this will be your A and B terminal, right? If we will be able to find out the current in this branch, okay, if we are able to find the current in this branch, then we can calculate the voltage across this resistance. All right, so we have to find out the voltage across this. Okay, so whatever the voltage across this, that will be your voltage across this open terminal. Okay, so let's say the current flowing here, that is total current in going into the circuit, that is I. Okay, and this current is divided here. Let's say this is your I1 and this is your I2 current. All right. Okay, to simplify this circuit, okay, we can write this circuit like this. We have this 12 volt, and this is 2 ohm. If you see here, this current, like this I1 current, is not going to a terminal A because it's an open terminal, right? So the whole current, I1 current, is going to in this it will be the same as in this resistance and this resistance. All right. So it means the current is same. Then this 4 ohm and this 4 ohm will be in series. Okay, so we can write this whole circuit like this. So this in series, so it become a 8. Okay, so this will be the, so this is 4 and this become the 8 ohm. All right, so this is the terminal A and B. Okay, now here if you see this figure, now this 4 and 8, they both are in parallel. So they are in parallel. So this 4 ohm is parallel with the 8 ohm. Okay, so what we are going to find out the total current. Okay, so the total current for this circuit, you can write here, this will be your 4 and 8 will be your, you solve this, it will be 4 into 8 on 12. Okay, so it will be your 8 by 3. This is simply 8 by 3. Okay, so you can simply write this is 2 ohm and it will be 8 by 3 ohm, and you have a 2 ohm and then you have a 12 volt voltage. Okay, now simply apply the KVL, you will have the total current in the circuit. Okay, so this I will be here. Simply apply the KVL in this loop. So you will have, this is 12 upon this 2 plus 2 plus 8 by 3, because all our value are in a series, right? So it will be 12, it will be 20, and the top is 3. Okay, so if you simplify this, it will be like this is 10 and this is 6, so it will be your 1.8. So now you have a 1.8 ampere current. So the total current in this circuit is 1.8 ampere. Okay, now you have the current, so you can make this circuit. Okay, so again, just make the circuit. So this is your 12 volt. Okay, so we have this. So this is your, you see the circuit. Okay, so now you have the total current. Okay, make this in that way. It will be easy. This is your 2 ohm and this is 2 ohm. And this will be the 8 ohm. Okay, so this is 4. The current is here is I. This current is going here is I2. Okay, and the current here is I1. So if we apply the current division rule in this section, we can determine the current I1 because we know the current total current I. So if we apply the current division rule, so current division rule says what? If we have this circuit like parallel combination, if you have 2 resistance, that's total current is going here. That's the current is there is I1. Okay, and this current is I2. And let's say this is your R1, R2. In the current division rule, if you're going to find the current value of this I1, that will be your I into R2 upon R1 plus R2. Okay, so this is called the current division rule. So once you will have this I1 value, so you can find out. So I1 here is what will the I1? I1 will be for this resistance and the current, the total current that we had determined earlier. So it is 1.8 ampere, right? So divide by this 4 plus 8 will be 12. So you simplify it, it will become around 0.6 ampere. Okay, now you have the current that is flowing in this 3 is a 0.6 ampere. So you can again write this circuit like this. The previous one, there is your 12 volt, 2 ohm. This is 2 ohm. This is 4. And this is 4 ohm and this is 4 ohm. Okay, and now this is the terminal A and B. Now we know the current in this, that is your I1 that we have calculated. So when we know the current I1, then we can find out the voltage in this terminal. So this VAB will be your I1 into this 4 ohm, right? So this 4 ohm, so that will give the current voltage across this terminal AB. So it's a 4 into 0.6. So that will be your 2.4 volt. Okay, so that is your VTH. Now you have the VTH and RTH. Okay, so now you have VTH and RTH. So what is Thevenin equivalence? Thevenin equivalent says it will be the Thevenin voltage and the series connected RTH. All right, so we have the RTH and this VTH. Okay, now you can connect your load. Okay, that is your RN. So we know the value of this, that is your 1.8, right? And this VTH is 2.4 volt, right? Let's say the RL value is given to, let's say it's a like 1 ohm, or maybe it's like 1.8 ohm, 1.8 ohm, for example. Okay, so if you apply the KVL in this loop, you can find out the load current, that is IL, and the load voltage. Okay, so first find out the this load current. So apply the KVL in this loop. So you have a 2.4 minus this 1.8 plus 1.8 into I is equal to 0, right? So now you can have this I is equal to, that will be your 2.4 divided by this 3.6. All right. So now it will be a 2/3, or you can say it's a 0.6 ampere current. All right. So in this circuit, you have a 6 ampere current. Now you know the load current. Now you can find out the load voltage, VL is equal to IL into RL. All right. So 0.6 into 1.8. Okay. Right. 8. It's 1.08. Okay. So that will be your around that. This will be your voltage. So okay, so that will be your load voltage. So let's, in this way, you can find out the your load voltage across this. So and if you want to find the power, so PL will be your VL into IL. In that way, you can find the power dissipated in this load resistance. By putting this value, you will get it. Okay, so in this way, you can apply the Thevenin theorem, and you can find the voltage and the current in any element. So like in a summarized way, we can say that, okay, if you have any complex network, so identify the element where you are going to find the voltage and current. So just remove that load of the element and find out the RTH and the VTH. So just following this steps, you can have you can simplify your any complex network using the Thevenin theorem. Okay, if you have any questions, just put in the question in the comment box. Thank you.